Hello again, it's me, Nathan Mikulski. I'm going to give you a lecture over our second topic, which is static failure. Alright, let's start this off with this idea, right? Or it's not really an idea, it's kind of more of a proven fact. And that is, plastic deformation or yielding is mainly caused by shear stress. So in this unit, we're going to analyze stuff that goes on with stresses, mainly shear stress and stuff. And this statement leads to a focus of static failure on ductile materials. Now, there's three main criteria for yielding. The first we'll talk about is the max shear stress criterion. The max shear stress criterion stems from the Mohr circle, like we have here. This Mohr circle is just a basic one with given shear in the y, shear in the x, or shear in the xy, and then regular stress in the x and regular stress in the y. Now, we were given this stuff here, which leads us to these 2 points. What we want to get is these principal stresses, which is sigma 1 and sigma 2. We are given an equation for sigma 1 and sigma 2, which goes as follows, which we derived from making that 2, so this is kind of just re-bringing that up. So sigma 1 and sigma 2 equal sigma x and sigma y. Sigma x plus sigma y divided by 2. Now that quantity is either added or subtracted, which gives us the added case would be sigma 1, subtracted case would be sigma 2, the square root of sigma x minus sigma y over 2, quantity squared, plus sigma x, or plus the shear in the xy squared. Okay? Now those give us, like I said, these two principal stresses. But how do we get the principal shears? Well, there's another equation simply derived from making that, which is actually just so happens to be the latter part of this equation. So once again, it'll be either plus or minus, the quantity, or the square root of the entire thing of sigma x minus sigma y over 2 squared, plus tau xy squared, or the shear of the xy plane squared. Now, this will lead to our sigma max. Our sigma max is important for determining, our max shear stress criterion. Now, what is this all leading us to? Well, it's leading us to developing factors of safety. Now, factors of safety are important in engineering because you want to be able to build something without always pushing it to the edge, pushing it to the limit of materials properties, materials capabilities. So we always try to factor in a factor of safety that isn't cumbersome to what you're planning, but also allows for, a safe margin. Now, how does this factor in here? Well, this is the max shear stress criterion. It's going to be based off of our factor of safety. Our factor of safety is our SY, or our yield strength, divided by 2, and that quantity divided by our tau max, which was calculated here. Now, what does that really mean? Well, like I said, it's just giving us a kind of a buffer and like an amount that we want to calculate in to give us a factor of safety. Now let's look at it in an example. Here we have an example of a rod attached fixed at one base with forces applied in the x, or the x, y, x and z directions, and also a torque applied to it. We were given the criteria of, we're going to find n with this first method first. Now, we are given that it has a diameter of 15 millimeters and a length of 100 millimeters, with this given force in this direction as 0.55 kilonewtons. The force in the x direction is being 4 kilonewtons, and the tensile strength, or the torsion, being 25 newton meters. And we're also given the yield strength is 280 megapascals. First, we need to find stresses in our principal directions. We can find that by using the simple stress equation, which is force over area. In this case, it'll be P over A. And it'll reduce to this, which would be P over pi over 4 d squared, which will equal 4,000 newtons, which is stemming from our 4 kilonewtons, divided by pi over 4 times 0.015, which is 15 millimeters, converted to meters, squared. And that gives us the stress in the x direction as being 22.6 megapascals. Now that we have that, we can apply our max shear stress criterion. First, we know that we have a shear in the torsional direction, and the shear in the, we have a shear stress caused by shearing and the shear stress caused by the torsion. The shear stress caused by the torsion we can find by this equation here, which would be T times D over 2 over J. Now, J equals pi D over 4 divided, or pi D to the 4th divided by 32. Now, plugging these two in together, this equation reduces to 16T over pi D cubed. When we plug in our numbers, we'll plug in 16 times our T from up here, which is 25 Newton meters, divided by pi times 0.015, and we're going to get 37.7 megapascals. Now, our shear stress caused by the shearing moment is 4/3 times VA, 4/3 times V over A, which is going to be 4/3 times 0.55 kilonewtons divided by pi over 4 times the diameter squared, which is going to give us 4.1 megapascals. Now, how do we find the shear in the XY direction? Well, we take the difference of these two. In this case, it'll be 37.7 minus 4.1, and we're going to get 33.6 megapascals. Now, we're going to plug that in to our equation that we found here to find our maximum shear. And the maximum shear is going to be the larger of these two values. So we're plugging it in. We're going to get the square root of 22.6 squared over 2 plus 33.6 squared, and we're going to get the shear max is 35.4 megapascals. Now, we're going to plug all of that plus this this material property into our safety factor equation. And we're going to get SY, or the yield strength, over 2 divided by the max shear stress, right? And that's going to be 280 megapascals divided by 35.4 megapascals. And that's going to give us a factor of safety of 3.96. That was the max shear stress criterion. Now we're going to move on to the distortion energy criterion. The distortion energy criterion, or octahedral shear stress, it's based from the octahedral shear stress, is another way of finding a factor of safety, but it differs from the maximum shear stress criterion. Now, taking a look at the octahedral shear stress, we are getting it from trying to expand like a unit, or basically a chunk of the material that we're going to be analyzing, and giving it more areas and twisting and finding it till we get the max shear stress, or the maximum normal stress being applied on one of the main faces. Now, the octahedral shear stress is useful, but the derivations are very long, and honestly, it's easier just to use the distortion energy criterion. But they lead to the same result, just the distortion energy criterion is a lot easier to use. So, let's take a look at the distortion energy criterion. Again, it's going to be based off of a factor of safety given here. Our factor of safety is going to be the yield strength over sigma prime. Now, what is a sigma prime? Well, our sigma prime is being derived from these equations, which are based off of derivations from the octahedral shear stress, right? So, if we're going to look at it, sigma prime based off of a principal stress, we're going to have the 3D version being this, which is sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared all over 2, and then that quantity to the 1/2 power. Now, similarly, the 2D case is going to be sigma prime is sigma a squared minus sigma ab plus sigma b squared, all quantity to the 1/2 power. Now, that's based off the principal stresses. You don't always necessarily have principal stresses. What may be easier is using XYZ components. So the 3D version of the XYZ components is 1 over root 2 times the big quantity of sigma x minus sigma y squared plus sigma y minus sigma z, or sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 times tau xy squared plus tau yz squared plus tau zx squared. That quantity, all of that to the 1/2 power, except the 1 over root 2 is outside of that. That's a little complicated, but luckily we have more of a 2D analysis, which works more in our favor. That 2D analysis will be sigma prime equals x squared, or sigma x squared minus sigma xy plus sigma y squared plus 3 tau xy squared, all the entire thing to the 1/2 power. Now, where is that going to come into play? Well, let's take a look at this example, but work it with these properties, or looking at it from the distortion energy perspective. So as we go through this, right, we need to find our sigma prime first. And we can find our sigma prime based off something we found previously, which is our sigma x and our sigma y. So that means we're going to use this x, y, z components, right? So plugging stuff in, we have this 22.6 is our sigma x, found before. We have that quantity squared, and in this case at A, there's no normal stress in the y direction, so that would be 0, 0, and we're just going to plug in our tau xy, which was calculated before also. We're going to 3 times that tau xy squared to the 1/2. Now, plugging that in, we're going to get 62.43 megapascals as our sigma prime. And to find our factor of safety, we divide our yield strength divided by that sigma prime. So it'll be 280 megapascals divided by 62.43 megapascals. We get a factor of safety of 4.84. Now, you may be asking, what's the difference between, or why do they have different results? Well, it's because they're looking at it from different perspectives. And you may be asking, which one should I use? Which one should I use? Well, sometimes it depends on the scenario, and sometimes it may be better to go with a higher factor of safety, and sometimes it might be better to go based off of the max shear stress as like a lower one. It's all relative to what information you have and the scenario you're looking at. Now, one more component, or the third component of the three main yielding criterions, is based off of the Coulomb-Moore theory. The Coulomb-Moore theory works based off of Moore circles. So shown here, we have 3 different Moore circles, all superimposed onto each other. Now, this first one, this little guy over here, is based off of tension. This bigger guy over here is based off of compression. And this one in the middle here is based off of torsion. Just straight. And each of those is based off of straight tension, compression, and torsion, right? So, superimposing them into each other, we can apply a Moore failure curve to them. So basically, kind of as it comes through here and touches each of these circles and goes through. Now, as we're applying that, we can approximate those curved lines to the Coulomb-Moore failure lines, which are these straight dotted lines here. And those are going to help us to find our principal stresses that we would need to, say, find a factor of safety later on. So, or find the other principal stresses. So we're going to call our sigma 1 as here, and our sigma 3 here as on the edge of the torsion circle. Now we're also going to find our negative SC here and an ST here, the torsional strength and the compression strength. Now, the tension strength and the compression strength. Now, we can set through a bunch of derivations in geometry. We can define this relation here. The sigma 1 over the tension strength minus the sigma 3 over the compression strength. Set that equal to 1, and we can find any of these values given, say, 3 of the others. Now, what if we have to base something off a factor of safety? Well, we can do that here. It's by simply replacing that 1 with 1 over n to find a factor of safety, or use a factor of safety to find one of those other stresses that will be allowable. Now, this is just a graph of this kind of looked at in a different perspective. So we can have sigma in one direction and sigma in the other, and we're going to base it off of the tensile strengths and the compression strengths. Try to find something in the non-failure region, which is defined by this 8-sided shape right here. Now, let's look at one last example to try to really drive home the first 2 components. So given a yield strength of 200 megapascals, an ultimate tensile strength of 275 megapascals, and a yield strength and a yield point of 207 gigapascals. We are given this stress element with a tensile force in the y direction of 100 megapascals, tensile force in the x direction of 50 megapascals, and a shear force of 25 megapascals. So first, let's draw the Moore circle. So we draw a Moore circle based off of our certain equations, right? And we have sigma 2 and sigma 1 and a sigma 2 defined. and a sigma 3 being 0. Now, doing more circle calculations based off of the radius that we can calculate, we get that our sigma 1 is going to be 75 plus 25 square root 2, basically plotting these from the Mohr circle, and then our sigma 2 is 75 minus 25 root 2. And like I said, our sigma 3 is 0 because it's lying at our origin. Now, let's define our shear max also as sigma 1 divided by 2, so it's going to be 75 plus 25 root 2 over 2. Now look at it through the distortion energy analysis. Again, that would be N, or a factor of safety, being SY, the yield strength, over the sigma prime, or our principal stress, right? So our sigma prime first is what we need to define, and that's going to be x squared minus sigma y plus sigma y squared plus 3 tau xy to the 1/2 power. Now plugging in our numbers, we get a value of 96.82 megapascals. Plugging that into our safety factor equation, we get 200 divided by that sigma prime, and we'll get a factor of safety of 2.06. Now, let's compare that to the max shear stress theory. Plugging in our equations, like we found our tau max already, plugging that into our equation, which again was N equals SY, or the yield strength, divided by 2, that quantity divided by the max shear. So that would be 200 divided by 2 divided by 75 plus 25 root 2 over 2. Doing some math, it reduces to 200 divided by 75 plus 25 root 2. That gives us a factor of safety of 1.81. And again, they're different because they're analyzing different things, but both are equally important to finding a factor of safety, and again, they depend on your scenarios. Thanks for watching. Have a great day.